Let's look at the sine and cosine functions, just the plain sine, plain cosine functions, and they look just like this. And you can see that they are nearly identical. They have the exact same kind of behavior. It's a little different because this one starts at 0, this one starts at the peak. But really all that is just a shifting, right? A phase shift off. If I draw a phase shift like this, you can see that I get sine on the cosine graph. So that tells us that sine of theta plus pi over 2 equals cosine. So we have this identity. And also, meaning by the same reasoning, sine of theta equals cosine of theta minus pi over 2. So there's these two identities that relate sine and cosine. They're actually the same graph, just shifted a little bit. These are not the only kinds of identities we can find with these two things. First off, if we look at this graph, you can actually see that sine is, if I go around 180 degrees, we have the exact same point. 180 degrees, exact same point. Sine is an odd function, so we have this identity. Sine of negative theta equals the negative of sine theta. Cosine is even, and just flip it right across the y-axis. So we have that cosine of negative theta equals cosine of theta. And you just remove the negative sign. Okay, now we also know, of course, the reciprocal identities. These have been well known, but specifically the fact that tangent is the same thing as sine theta over cosine theta, right? Sine is the y, and cosine is the x. So tangent is y over x. It's the same thing. This we already knew is 1 over sine theta. Same thing with this one. And then this is just the reciprocal of tangent, so cosine over sine. Now we're going to consider the unit circle. Specifically, you know, the normal unit circle idea that cosine is x, sine is y. So we know cosine is this leg down here, and sine is this leg here, with this being theta. And this is a right triangle, so we know the Pythagorean theorem fits x squared plus y squared equals 1. That's the same thing as saying cosine squared plus sine squared equals 1. We can take this equation, and what I'm going to do first is I'm going to divide everything here by cosine. If I do that, this of course just goes to 1. This becomes sine squared over cosine squared, and this one becomes 1 over cosine squared. So we have 1 here. I can take the square out of both and put it over the entirety. This is tangent. And 1 over cosine is secant. So instead of cosine squared plus sine squared equals 1, we now have 1 plus tangent squared equals secant squared. That was when we divided it by cosine squared on everything. Let's divide next by sine squared. Doing that gives us cosine squared over sine squared. This just becomes 1, and 1 over sine squared. Doing the same process, this is just cotangent, and 1 over sine squared, that's cosecant. So we have cotangent squared plus 1 equals cosecant squared. And these are all called the Pythagorean identities because they all come from the Pythagorean theorem. All right, we can simplify statements down using these identities, and we're going to see a lot of these identities, and they're going to be fairly useful in random ways. And you can simplify statements down, you can simplify expressions, you can make equations easier to solve by using these identities. And one of the things that can help out a lot is to change everything into sines and cosines, because then you can see what probably the most readily able to cancel with each other. So I'm going to do that here. In this first one, I'm going to change cosecant to the reciprocal. Cosecant is 1 over sine, so I'm going to write it as 3 times sine cubed t times 1 over sine of t. plus cosine squared t. On this one, I don't like the fact that this has a negative t in it. I'm going to remove it using the fact that cosine is an even function, which means cosine of negative t is the same thing as cosine of t. I can just remove it. Okay, now I can see here, well, one of these powers is going to cancel with this, and I get 3 sine squared t plus cosine squared t plus 2 times cosine is cosine squared t. And you can change however you want. I can change sine squared to cosine, or I can change cosine squared to sine. I'm going to change sine squared because there's more cosines here, but it really doesn't matter. Using the Pythagorean identity, sine squared plus cosine squared equals 1. That means sine squared equals 1 minus cosine squared. So I get 3 times 1 minus cosine squared t. That's all what this statement is. It's been changed here. These are the same thing, so I can add them together. 3 cosine squared t. Distribute the 3. We get 3 minus 3 cosine squared t plus 3 cosine squared t. Those cancel. And it simplifies down to 3. Okay, write the expression in terms of cosine of x. So we want specifically cosine. And to do that, I'm going to first change tangent to sine over cosine. It's going to get me closer to cosine, I think. So let me just try that. And a lot of times with this kind of mathematics, if you're not sure what to do, just try something. Just try an identity, see what does work, see what happens when you try it, and then you can go from there. That typically will give you some kind of idea on how to proceed. So I see that I have 2 fractions. Typically, we don't like to have fractions, in with the addition. Let's combine them into 1 fraction. We'll do that by getting common denominators. Okay, this one needs a 1 plus sine x. Okay, that's going to give me cosine squared on the left-hand side plus, it's going to be sine x plus sine squared x all over. I'm going to leave it as cosine x times 1 plus sine x. All right, we want in terms of cosine. So let's change this into cosine. So this is going to be 1 minus cosine squared. I just want to try that and see what happens. So we have cosine squared x plus sine x plus 1 minus cosine squared x. See, 1 plus sine x is on bottom still. Now these actually cancel, which is nice. And 1 plus sine x, 1 plus sine x, those cancel to give us just 1 on top. So we have 1 over cosine x. So that was the right move, changing that to that. You could change this to sine, to 1 minus sine squared x. But if you did that, I think when you were to continue, you may be able to find a way back to this same spot. I think it would take longer though. This, of course, is what they wanted. This is, of course, secant of x, but they wanted it in terms of cosine. So we're going to leave it as 1 over cosine x. All right. And this is a classic trig proof. So we have a statement that says, is this side equal to this other side? And we're going to prove or disprove. And you prove it by showing that one side equals the other side in some fashion. You disprove it by showing, like, for instance, if I took the left-hand side of this thing and I simplified it down and I got sine theta, then I'm saying sine theta equals sine squared theta. This is not true. This is a disproof. You want it to be that the one side, what I want to see is I want to see this become sine squared theta, or this side to become this whole fraction here. And I think it's easier to work with the larger side and break it down. It really depends on the situation though. If you're getting stuck on something, try working with the other side. Try doing different things. I'm going to work with the left-hand side and see what I get. So I get cosine squared theta minus sine squared theta over 1 minus tangent squared theta. And cosine squared minus sine squared, this is almost a Pythagorean identity. It's actually cosine squared plus sine squared. So I can't make that immediate change to just being 1 on top. But I can take, let's say we move, since I want sine squared, I'm going to change cosine to sine using the Pythagorean identity. This is the same thing as 1 minus sine squared. So we have 1 minus sine squared theta minus sine squared theta. Tangent, 1 minus tangent squared. If we go back to the Pythagorean identities, we have this one here. Secant is 1 over cosine. Since it's squared, that means I can change that to sine again, which might get me a little bit closer to where I want to go. So I'm going to use this identity. 1 plus tangent squared equals secant squared. But I have just tangent squared. I have 1 minus tangent squared. So I'm going to use the identity that says if 1 plus tangent squared equals secant squared, then that means that tangent squared equals secant squared theta minus 1. So this is just going to be secant squared theta minus 1. Okay, I need to distribute the negative. That's going to give me, we'll see, 1 minus 2 sine squared theta on top. On bottom I have, let's do 1 minus secant squared theta plus 1 over 2 minus secant squared theta. Okay, secant squared is 1 over, let's see, it's going to be cosine squared. Cosine squared is one minus sine squared theta using the Pythagorean identity once again. And now I can get common denominators over 1. That's going to give me 1 minus 2 sine squared theta over 2 times 1 minus sine squared theta minus 1 over 1 minus sine squared theta. Okay. I feel like we're getting close. We'll see what happens. I'm going to multiply by the reciprocal and just see what it takes me. So we have 1 minus 2 sine squared theta times 1 minus sine squared theta over 2 times, you can actually distribute that 2. It's going to interact with the negative 1 there. That's going to give me 1 minus 2 sine squared theta. Well, that's interesting because these cancel. And I get 1 minus sine squared theta. But 1 minus sine squared theta does not equal sine squared theta. So this does not equal sine squared theta. So therefore, these cannot be equal. This is not a valid trig identity. So with that, that's a proof that this identity is not true. This is not equal. Instead, if it were 1 minus sine squared theta, that would be a valid proof. Okay, give it a try in numbers 1 and 2.